Okay, welcome to another Orbiter 2010 video. Today is Friday, July 26th, 2013, and this is going to be a continuation in the video series that I'm putting together that has an emphasis on users who are brand new to Orbiter. I've kind of started calling it the Absolute Beginner Guide. Now, before we jump right into the next part of the video series, I just want to briefly mention that this video is kind of special to me because this is the first video that I'm recording after my lung transplant. For those of you who don't know, I'm just going to cover this very briefly. I was born with a disease called cystic fibrosis. If you're interested in that, you can look it up on Wikipedia and read a little bit about it. I won't bore you with the details. But over the course of my life, my lungs have actually degenerated so much that it was difficult for me to do much of anything at all. In some of my previous videos, if you go back a year or so, you'll see that there were actually a lot of videos where I was struggling just to talk because I was so out of breath that I couldn't even get through the videos very well without just being extremely winded, let alone any type of activity, getting up and taking the mail to the mailbox or taking the garbage out. Any of these types of tasks were just extraordinarily difficult for me. So on June 22nd, around 11 p.m., I got a phone call letting me know that a suitable donor had been found. And this was actually the third time I had gotten such a call, but the first two times things just didn't work out. And when they told me when I was going through the lung transplant evaluation process that there would be the possibility of these false alarm calls, and that happened to me twice. But on the third call, I got down to the hospital, called my family obviously, and everything went well. And I'll just briefly put up a couple of pictures here so you can see. This was me the day after. I believe this was taken just the morning after the transplant. You can see, obviously I'm pretty out of it. I don't really know what's going on. I got a feeding tube stuck in my nose. I've got another feeding tube actually in my neck. They were giving me two types of different forms of feeding because I couldn't eat. The bandages over my chest are actually covering the incisions where the doctor had actually cut across the chest to put the take the old lungs out and put the new lungs in. And here's one other picture I'll put up. This was taken one of the last days that I was in the hospital after all the bandages have come off. Obviously you can see the incisions there around the pectoral area. And so yeah, that's it. That's all I'm going to say about that. It is quite a miracle to me to be able to be here just 1 month later, feeling good and feeling up to talking and doing this video already. I've been missing Orbiter for sure. So that's it. That's all I'm going to say about that. Now, in the last video that I did, which I don't even remember when I recorded it, to be honest, it was quite a while back, we talked about getting into a specific orbit. We talked about how when you take off from the ground, at Cape Canaveral or any other launch site, you can get into a generic orbit, by going to a heading of 90 degrees or some other arbitrary heading. But when you need to get into a specific orbit, which you do need to do if you're going to rendezvous with the space station or if you're going to go to the moon, then you need to get into a specific orbit. So we talked about how to do that, but we left off with our Delta glider here. You can see, if I kind of come over here a little bit, our Delta glider is now in orbit and it's in plane with the ISS. That's kind of what we talked about in video 3 and video 4, was how to get into a specific orbit so that our plane would match the plane of the object that we're trying to rendezvous with. Now, being in plane with the object that you're trying to rendezvous with is all well and good, but there are still problems that we have to overcome before we can actually catch up to that object and dock with it. Let's take a look at Orbit MFD. Let's bring up Orbit MFD on this side. And as usual, we'll change projection from ECL to ship, which we talked about, I believe, in the probably video 2, I think it was, how in almost all cases when you're new and you're doing things, for starters, in almost all cases, you're going to want the projection to be set to ship, and we toggle that just by pressing the PRJ button. Now we will kind of introduce a new concept here, which will be that we'll be able to look at the orbital elements of the ISS in addition to the orbital elements of just our ship itself. And it might actually be less confusing if we do it this way. We'll bring up orbit not only on this side, but we'll have it on this side as well. And these operate independently of one another. So in other words, you can see here I've got projection set to ship, and over here it's set to ECL. These do not conflict with each other. Setting something over here does not mean that it's going to update this side also. These work independently. So what I'm going to do on this side is I'm going to just change the projection of the ship. And actually, one thing I forgot to do was to change the distance readout. We talked about that in one of the previous videos as well. Here we have the distance readout as planocentric, so it's telling me what my altitude is, my APR here. It's telling me what my altitude is from the center of the Earth out to my altitude, and that's not terribly useful in most cases. It's a little more comprehensible if we toggle that to DST, or rather if we press DST to toggle that to the altitude readout. So now it's telling me what my altitude is, not from the center of the Earth out, but it's telling me what my altitude is from the ground up. So from this gray part here up to here is a difference of 206 kilometers. That's what my current altitude is. And I'm going to make that change on both sides. Now what I'm going to do on this side is I'm going to press TGT. And remember, we discussed that when you select targets, you can't press the TGT button and then click on that window. It just doesn't work that way. What we have to do is use the arrow key to go down to, say, spacecraft, and then right arrow over to ISS and hit enter. Now I have the ISS targeted in this MFD, and it kind of might help again to have these separately so that you can see on this side just your ship. This is just the information for our Delta glider, and over here we have both. We have the information for our Delta glider combined with the information for the ISS. Now the reason I want to show this is because it illustrates what the difference is in our altitude. Remember, when we got into orbit around the Earth, we went for an initial apoapsis, a high point of about 200 kilometers. We wanted to hit somewhere in that range. That's generally what you'll go for. If you're specifically going to the ISS, it may not even be a bad idea to shoot for a target altitude of 300 kilometers, because as you can see, the ISS orbits at about 365 kilometers, give or take. Currently it's at 367, the high point's 370, and the low point of the ISS is 357. So targeting an initial altitude of about 300 kilometers may not necessarily be a bad idea. There are reasons to be lower, like we're down here at 200, and we'll kind of get into maybe a little bit of that later. So here we have this issue where our high point is 206 kilometers and our low point is 206 kilometers also. There's only a difference of 600 meters between our high point and our low point. And again, we can also see that over here. And if it helps eliminate confusion by not having the additional data, then you can look at just this side to reference how high we are in our orbit. Now, the ISS is above us by over 150 kilometers. Even at the lowest point, it's still 150 kilometers above us. So what I kind of want to show is a few things here. Obviously, in order for us to rendezvous with the ISS, we're going to have to raise our altitude. And raising and lowering our altitude is the only thing I'm going to cover in this video. I don't want to talk about sync orbit, MFD, we'll get into that later, and I don't want to talk about any other aspect of rendezvous. So we're not actually going to catch up to the ISS in this video. It's going to take, another video out in the future yet, maybe even 2 more before we actually catch up to the ISS. But we need to understand all of the points of raising and lowering the orbit. We need to know how that works. And if we don't know how that works, then we can get into some trouble later on. But before we really worry about raising and lowering our orbit, let's first of all just use a little bit of time warp so we can see what's going on with our orbit stuff here. Now, I'm also going to bring up map MFD on this side. Hopefully, you can understand what's going on over here well enough now that you've seen these, now that you saw the orbit MFD without the ISS on that side compared to the orbit MFD with the ISS on this side. So hopefully you understand what all this information basically means. And again, I don't mean to say that you know what all these numbers mean, obviously, because we haven't covered that yet. But you understand the basics. You understand that we are at 200 kilometers. That's us. That's our green line. And you understand that the ISS is much higher than us. That's the yellow. The ISS is at 368 kilometers. So let's just do a bit of time warp here, and let's watch what happens without worrying about raising and lowering our orbit. We're not going to do any of that yet. Let's go out to 1,000 just because 100's a little too slow. Actually, let me go do this. Let me press Control F2, and so I can get some finer control over the time acceleration, because I don't want to go all the way from 100 to 1,000. I want to go maybe to 300. Yeah, that's good. And you can see what's happening is that we are orbiting the Earth at a couple hundred kilometers, and we're happy at that altitude. The ISS is up there above us at 300 kilometers, and if you pay attention, and as you can see in the map MFD, we're going around the Earth, we are actually catching up to the ISS. And why is that happening? Well, let's come back out of time warp for a moment and understand why that's happening. Let's introduce a couple of new numbers that we can look at here in Orbit MFD. Let's look at T right here. T, this is just time. And time is quite simply the amount of time it takes us to complete one full orbit. In the time that it takes us to complete one full orbit, this is us, this is the green, this is our ship. It takes us 5,309 seconds to complete one full orbit. Now, let's bring up a calculator and punch that number in just to get something more meaningful, divided by 60. So it takes us 88.4 minutes, or about 88.5 minutes, to circle the Earth one time. Whereas it takes the ISS 5,500 seconds. Notice that's larger. It takes the ISS almost 200 seconds more than it does us to circle the globe one time. And if we put that number into our calculator, 5,500 divided by 60, you can see it's 91 minutes. So it's about 3 minutes difference. So for every orbit that we go around in 88 minutes, it takes the ISS, 91 minutes. That's why we're catching up. We're catching up because we're going a little bit faster than the ISS. And the reason we're going a little bit faster is because we're a little bit lower. We're down lower than the ISS. And this gets into Kepler's laws of orbital mechanics. If you're interested in that, you can do a little bit of Google search. Just Kepler's laws of orbital mechanics, I think, will be fine, and you'll find some information on that. But the reason that the reason our orbital period is lower, let me introduce one more number in this column, is because our velocity is a little bit higher. Our velocity is 7,785 meters per second, whereas the velocity of the ISS is only 7,700 meters per second. And again, you might be wondering, well, why is that? Why are we going faster than the ISS? Well, it's an inverse square law. I believe that's the correct terminology. The farther away you are from the central mass, the slower you go, or the less gravitational pull that body has on your vessel. So just due to the fact that the ISS is 150 kilometers farther out than we are, it's traveling slower because the gravitational influence of the Earth isn't quite as high as it is on our vessel down here at 200 kilometers. So that small difference in altitude means that the ISS is going to travel a little bit slower. That actually works out pretty well for us because that allows us to catch up to the ISS without spending any fuel energy. We don't have to do any engine burns in order to catch up to the ISS. All we have to do is let some time pass. And let's just watch how that happens. Again, let's go to 100. And then I'll bump this out to say 200 or 300 just to speed it up a little bit. 1,000's too much. So let's go 300 and maybe even 400. And while that's catching up, I'm just going to take a sip of water. And here we are. You know, we're going around the globe. We're at 88 minutes. The ISS is taking 91 minutes. So each orbit that goes around, we're catching up to it 3 minutes at a time. And we're almost there. Let's go back to 1x. And I'm not quite there yet. Let's go a little faster. And we're nearly there. Okay, we're really close. Let's go back to 1x. Now you can see, and if we zoom all the way in on MapMFD, you can see that we are very close to the exact same spot as the ISS, and we're going to continue catching up to it until we actually overtake it. And you can also see that indicated here in Orbit MFD. We are now, the ISS, if we had a powerful enough pair of binoculars or telescope or something, if we were in the space shuttle, we could, you know, kind of look almost straight up and see the ISS passing over top of our heads here in just a moment. If we go to maybe 10x, you can see that distance closing down because we're just getting very close there. And here in just a moment, we're going to actually overtake the ISS. See us catching up. Let's go to 20 just to speed that up a little more, and there we are. And now we're directly below the ISS. And now we're passing. We're still lower than the ISS, obviously, but we're now passing the ISS. It's now in the rear view mirror, so to speak. Okay, so now hopefully you understand kind of the basics there of, you know, how the objects work in terms of their altitudes. You know, the Delta glider, being at a lower altitude, travels a little bit faster than the ISS, so therefore, you know, it's going to catch up to it. Now, it would also be the case, and hopefully you can kind of think about this logically, if we were at 500 kilometers instead of 200, you know, and let's say our orbit was basically circular like it is now. We can see our ECC again is 0.0000, which means we have a very circular orbit. If our PEA and APA were approximately 500 kilometers, that would mean that we would be 150 kilometers above the ISS. If that were the case, then the opposite situation would be true. We would be, our total time to go around the Earth would be higher than the ISS. It would take us longer because we would be above the ISS. It would take us longer to go around, and our velocity would be less than the ISS. So the reverse situation would be true. But now we need to talk about how we can raise our orbit and how we can lower our orbit, because we need to know how to do both. Refer to, let me find this real quick. If you go again, and I'll encourage this many times, to go to your orbiter installation and go to the dock directory and open orbiter PDF. And you're going to want to skip down to page, I believe it's page 95. Yes, page 94. And just kind of browse over this section called Changing the Orbit. We'll cover it here, so I'm not going to obviously sit here and read over this, but refer to page 94 and page 95, and it gives you some basic illustrations here so that you can to help understand what's going on. When we need to raise our orbit, what we need to do is we're going to add velocity in our direction of flight. This is very similar to what we did just to achieve orbit. If you recall, when we were trying to achieve orbit, when we needed to circularize our orbit, we had our PEA was negative 56 or something like that. And in order to circularize our orbit, we had to raise the opposite side of our orbit up so that it would be equal, to the high point of our orbit. And we did that by adding velocity in our direction of flight. And our direction of flight is prograde. If we kind of look at the external view here at the moment, which unfortunately it's not daytime, but our ship is kind of in this wonky orbit. And let me actually go around to the day side just so we have something easier to see. There we go. It's in this kind of wonky orientation. We're pointed out into space, in no real particular meaning, and that's because we don't have any autopilot turned on to keep our vessel oriented. When you're just doing basic orbits, you don't want to waste the fuel to have your autopilots on. You always want to shut those off because it uses small amounts of linear and RCS translation to keep the vessel oriented. So you want to turn that off when you don't need it. And right now our vessel is pointed out in this bizarre direction, in this useless direction. So if we were to add velocity right now based on the way our ship is oriented, we would be thrusting the vessel, that way. The thrust would be coming out from the back, and we would be pushing the vessel. We're saying that we're wanting to push it that way, and that's not the direction of flight. And you can clearly see that just based on looking at the external camera. The direction of flight is obviously this way. You can see the clouds coming by very quickly, moving this way. So we need to orient the vessel that way so it's toward our direction of flight. And again, we can do that very easily manually, or we can just press the prograde button. And for everybody that's new to Orbiter, I would just say go ahead and use the prograde button. A little bit of an advanced tip: using the prograde button isn't quite fuel efficient. It's not as fuel efficient as it can be, so just something to get you thinking later on down the road when you're really getting into Orbiter and you want to be as efficient as possible. You can usually save fuel by switching to the rotation thrusters, and we know which way we need to go because, again, the green triangle here indicates where prograde is at, and I can just, with a little bit of 1, I can get the ship moving in this direction, and I can basically wait, because if I'm not in a big hurry, because there's no atmosphere to slow the vessel down, it will eventually swing its way around, but that's going to take a while, and we're not going to wait. And since this is since this video is focused on new orbinauts, I recommend just pressing the prograde button, and you'll see that by doing that, it's going to orient the vessel automatically in the direction of flight, and that's what we need to have happen if we want to raise our orbit. And that's what we're going to do now. We're going to raise our orbit. We do want to wait until the vessel is completely settled, so you don't want to start raising your orbit when it's still pointing out here at 10, or if it's off center in the other direction, if it's still pointing up here toward 20. You want to wait till the autopilot has time to settle. So always think ahead. Know that it's going to take the autopilot 10 or 15 real seconds to get the ship in the prograde position. So when you're doing your maneuvers, make sure you leave yourself enough time for the autopilot to get the ship set in the correct position. Okay, now we're going to raise our orbit, and since we're not quite yet ready to talk about the actual rendezvous process, we're just going to pick the altitude of the ISS as our target altitude for raising our orbit. When we get into the actual rendezvous process, actually synchronizing our orbit, we'll get a more precise and specific altitude target. But for now, since we're just wanting to talk about the basics of raising and lowering the orbit, we're just going to pick whatever altitude the ISS currently happens to be at, which is 357.8. Now, what you don't want to do here is you don't just want to press the plus key and hold it, because that will apply so much delta V, so much engine thrust, that you'll end up raising your APA out to 400, 500, 600 kilometers or something crazy. You won't have really any control over it. What you want to do is kind of press the control key and hold it down, and then tap the plus key once, maybe twice, maybe 3 times, and you can see that we're adding just a little bit of thrust. You can see the vessel here, the engines, they're barely even lit up. And you can see here we've got just a little bit of main engine, and we're raising our APA slowly. We can control it very easily by putting in just a little bit of main engine. And we can, if it's too much, we can press Control and hold it, and press the minus key a couple of times to back it off. Notice we've already raised our APA from 200 kilometers to just over 300. So that's how we raise our orbit. We orient the vessel into the prograde position, and we apply the amount of main engine that we need. But again, we're going for an altitude of 357.8 or something thereabout. Now it's down to 6. So let's continue this. So I'm going to press Control and hold it. Now I'm going to tap the plus key 1 time, maybe 2 times. And now I'm done. I'm going to let go of all the keys. And when I get to about 350 kilometers, maybe a little bit more than that, I'm going to press the asterisk key. We're almost there. Let's go with that. Now I'm going to press the asterisk key to kill the engines. And I'm at 356.5. I'm almost at my target, but I'm not quite there. In order to get that last little bit of refinement, to get the last tiny bit of altitude that I want, the main engines, even at their smallest increment, are still too powerful to do any fine tuning. So what we want to do is we want to switch our RCS mode from rotation to translation. And again, we do that by using the slash key, the / key on the numeric keypad.
Translation.
Notice it just said translation, so I now have translation thrusters. That's what I want. If I press that key in here, rotation, I know that's the wrong one. I don't want rotation, I want translation.
Translation.
Now with translation thrusters, I can press the 6 key, that's the number 6 on the numeric keypad, and notice those tiny little bursts. It's adding in just a little bit of velocity, just a tiny amount, but that allows me to fine tune I can pinpoint my exact altitude with fine precision by using those translation thrusters. And again, when we originally said our target altitude was 357.8, so we're going to go with that. And as we get really close to that number, we can do even one more thing. Sometimes, believe it or not, pressing 6 with the translation thrusters is still too much thrust. It's unbelievable, but it can still be too powerful. So what you can do is you can hold down the Control key and press the number 6 and get micro bursts. These are very small bursts. They're 1/10 of the translation. And there we have it. We now have our target altitude, our target apoapsis rather, of 357.8. Now you'll notice that if you look very closely to our orbit lines here, and in fact let me bring up an external MFD to make this very large so that it's very obvious. So let me target the ISS here. And projection, oh, we already had it set. So okay, let me make this as large as I can so this is very obvious. There we go. You'll notice that our green line here comes around here and it starts getting closer and closer to the yellow line. That's because we raised the other side of our orbit. Over here, when you apply velocity at your current location, which your current location is wherever that green line is at, it has no impact on your current position. Whether you go retrograde or prograde, your current position doesn't change. Whenever you add or subtract velocity, it only has an effect on the opposite side of your orbit. So what we've done here by adding in that little bit of velocity, we've actually raised the other side of our orbit. So coming over here 45 minutes from now, the other side of our orbit is now approximately the exact same height as the ISS is at this position. And you'll also notice by doing what we've done here, by raising the other side of our orbit, if we compare, and I don't remember the number before, but if we compare our time, our orbital period has gone up. It was 5,300 and some seconds before. I don't remember the exact number. But it's now 5,400 seconds. It's a little bit longer. And the reason that our orbital period is now a little bit longer is because it's now one side of our orbit is now a little bit higher than it was before. So on this side of the orbit, we're still traveling at the same velocity, more or less, that we were before. But as we get out here and we get farther away from the center mass, the center of the Earth, we're traveling a little bit slower. And because we're traveling a little bit slower at this point, it takes us a little bit longer to complete one orbit. Now the ISS itself is still taking longer than us because the ISS is at that altitude on both sides. Notice the altitude over here of the ISS is still, out at 360 kilometers, and it's 350 or 360 kilometers on this side. Whereas with our orbit, it's no longer a perfect circle or close to perfect circle. Notice our eccentricity has gone from 0.0000 to 0.0114 because we now have a slightly elliptical orbit. We're now a little bit cockeyed. This side of our orbit is lower than that side. And the difference over here, and this side, we're traveling a little bit faster than we are on that side. Okay, now let's go ahead and warp time forward again. We're just going to press T. And actually, before I do that, I notice that I still have the ProGrade Autopilot on. And again, we don't ever want to use time warp, or at least we want to avoid it as much as possible when we have any of these autopilots on. So it's get in the habit of turning off autopilots before you do any time warp. But we'll go ahead and go around to the high side of our orbit. And we're getting close to that point. Again, the time to the highest point of our orbit is given to us here. That's APT, apoapsis time, or time to the apoapsis. That's how long it's going to be before we get to the highest point of our orbit. Now let's say that we want to balance our orbit, or basically balance it out. We want to bring up the opposite side of our orbit. We want to bring our eccentricity basically back down to 0.000 so that our orbit, the high point, or so that the low point of our orbit is about the same as our high point. Currently our low point is 205, it's 205 kilometers, and our high point is 357.8. We're getting close to that point, so we want to get into the prograde position because again, we need our vessel to be facing the direction of flight, and the direction of flight is prograde. So we're going to go ahead and use that ProGrade Autopilot to do that work for us. It's orienting the vessel. And there it is. And just like we did when we circularized our orbit after achieving orbital velocity when we took off, we're going to do the same thing here. That is, we're going to just put in a little bit of engine thrust in order to bring up the other side of our orbit. But we don't want to do that until the time to the apoapsis is really close to zero. Now, I do want to point out that the reason I say we don't want to do it until it's really close to zero is simply because this Delta glider has very powerful engines. If we were using a vessel like the Space Shuttle, we would actually want to start this type of thing much sooner because the Space Shuttle's engines are very weak, but because we are in the sophisticated and futuristic Delta glider, we have very powerful engines, so we can get away with waiting until the time to the apoapsis is almost at zero before we worry about trying to balance our orbit. And once we get down to say 10 seconds, we'll put in just a little bit of main engine and we'll watch the other side of our orbit. We'll watch our PEA go up. And then you'll notice that this green line over here will get closer to the yellow line because we're affecting the opposite side. Okay, we're at 5 seconds here, so I'm putting in just a few clicks of main engine, and you can see the opposite side of the orbit coming up, time to the apoapsis counting down. And I'm just going to watch that till it gets really close. We don't want to overshoot. There it is, 355.6. We're very close. So again, now we'll use linear translation, checking our RCS mode here, or if we're looking at this view, we want to make sure that RCS mode is not rotation but linear. And we'll press 6 just to bring up that last little bit. And now down to Control 6. And there we have it. We've got our apoapsis at 357.8 and our periapsis at 357.8. Eccentricity 0.00 So we now have an altitude that is very close to the ISS. We got into orbit. We got our plane perfectly aligned. Again, we'll bring up Align Plane MFD here. We got our plane perfectly aligned, so we're traveling around the Earth in the same plane as the ISS. And now we've raised our orbit so that we are at basically the same height as the ISS. Now, we can't rendezvous with the ISS yet. Unfortunately, it's not quite that simple. Because of the fact that we're now basically at the same height as the ISS, that also means that our orbital period, the time that it takes us to circle the Earth, is now almost exactly the same as the ISS, and our velocity is almost exactly the same as the ISS. This actually presents a problem for us because of the fact that we are at the same velocity and everything's the same as the ISS. We're almost stuck in front of the ISS permanently, and that's something that we'll address in the next video. This video is just going to be about raising and lowering the orbit. But you notice if we kind of warp time forward here, go to 100, go out to 1,000, it's kind of the case here that it takes a really long time now for there to be any appreciable difference between the ISS and ourselves, because our orbital velocity is almost the same, and again, our orbital period is almost the same. So you can see that it would take us, days and days and days, or maybe even weeks, to catch up to the ISS, or have the ISS catch up to us. So when we actually do the official rendezvous process, we need to take that into account. We need to take into account the difference in time between us and the ISS so that we can arrive at the altitude of the ISS, but also arrive at the altitude of the ISS at such a time as that our paths cross. But again, we're not addressing that in this video. This video is just raising and lowering the orbit. Now let's do this. First of all, let's go back to prograde and let's raise our orbit out to some arbitrary number. Okay, so instead of 357, which is currently, let's say 700 kilometers, just to give it a bigger number. And I'm going to do that by using a lot of main engine here. Notice my APA is going way up. Okay, we're getting pretty close to our target number, so let's not use the full power of the main engines. Let's just use a couple clicks of main engine. And my APA is, okay, that's almost 700, so now let's go to linear translation and get the last little bit of difference. And there it is, our APA is 700. So let's turn prograde off. Now remember, we only raised that one side of the orbit. This side of the orbit is still down to 357. So let's go around and balance out the orbit. Now we know how long it's going to take us to get to this point because of the APT value. So we'll press T and we'll just kind of watch that number. And we can also see the visual that when we get to this point here, that's when we're going to be at the high point. So let's warp time forward over to the apoapsis. We're getting closer. We're just 1,000 seconds out, but we're at a warp factor of 100, so it won't take long to get there. And when we're at about 100, we'll come out of time warp so that we can let the autopilot do its job. I went back to 10 when I got down to 200 so that I don't overshoot. And we're pretty close, so let's go back to real time. And let's press prograde and give the autopilot time to do its job. You don't want to wait till you're at 1 second before you do this, because you'll be well past that point by the time the autopilot has settled. Okay, we're pretty close. Now let's go ahead and warp time forward just a little bit more. We'll go ahead and leave the autopilot on here for just a couple of seconds. It'll be fine. We just don't want to warp time forward, by tremendous amounts with autopilots on. That's a bad thing. And again, we'll go down to maybe 10 seconds, about right there. And we'll add in just a few clicks of main engine. We don't want to overdo it. And we're raising the other side of our orbit. Our PEA is coming up. And when we get to about 680, then we'll kill the main engines so that we don't overshoot. Now we'll use linear translation.
Rotation.
That's rotation. That's not what I want.
Translation.
That's translation. That's the one I want. We'll use a little bit of translation to get the last couple of kilometers. And as we get to 699, we'll hold down control and we'll press 6 so that we don't overshoot. And we're pretty good right there. There's a little bit of difference, but never mind. We have our eccentricity down to 0.0000. So now we are above the ISS. We're above the ISS by a pretty significant amount, about 350 kilometers. Now let's take a look at what that means. Our orbital period, our total time, is now 5,917 seconds versus the ISS that has an orbital period of 5,500 seconds. Just one moment. Checking the time, I'm 41 minutes already. And our velocity is 7,508 meters per second versus the velocity of the ISS, which is 7,000, let's call it 7,700 meters a second. So because we're further out, we are traveling slower than the ISS. Again, do the Google search about Kepler's laws of orbital mechanics to understand a little bit more about that. And our velocity is lower. And if we, I'll illustrate this point here too, if we go forward in time, we are going to lag behind the ISS at this point. Notice this green line, that's us. It's actually starting to kind of fall behind the ISS. The ISS now is directly below us, which we can't really probably see in orbiter. Let me press F9 to see if I can see it. No, I don't imagine there's any way to actually see the ISS. But again, if we had, really powerful binoculars, we could go to the flight window here of the Delta glider and look basically down toward the Earth, and at some point we would see the ISS pass right below us, and it's going to pass in front of us because it's traveling faster. It's traveling faster because it's lower, it's closer in toward the Earth, therefore it has more gravitational pull. And you can see as we go forward at 1,000, it really starts to take off and get in front of us. This concept is really important to understand. It's not just dry, boring orbital information. In order to rendezvous with an object, you really have to understand how these motions work. The farther out you are, the slower you are. The closer in you are, the faster you are. And the faster you are, the quicker you go around the globe. The farther out you are, the slower you go around the globe. It's very important to understand these concepts. Last thing we'll talk about before we end this video is lowering the orbit. We know how to raise the orbit. We raise the orbit simply by pointing the vessel into the direction of flight, which is prograde, and we apply main engine as needed to bring up the other side of the orbit. And then to balance that out, we go around to that side and do the same thing. We burn prograde into the direction of flight to then raise the other side of the orbit to balance things out. Now, to lower our orbit, we don't really need to talk in as much depth about it because it's the same concept, but it's done in reverse. Instead of prograde, it's retrograde. It's that simple. So we'll go into the retrograde position to lower our orbit, and retrograde is simply 180 degrees opposite of prograde. So instead of burning into the direction of flight, we're going to be burning against the direction of flight. Once the ship settles, you'll get a better idea of what that looks like. Okay, we're more or less settled. Now you can see the Earth passing below us, and the Earth is, obviously moving this way, and our nose is pointing that way. It's pointing against the rotation, or it's pointing against, I should not say the rotation, but it's pointing against our direction of flight. Our main engine thrusters are now this way, so if we burn this way, we're going to be slowing ourselves down. We're going to be decreasing our velocity. So instead of adding velocity, we're going to be decreasing velocity. When we decrease our velocity, it's not going to have any impact whatsoever on our current position. This won't change. It will have an impact on the opposite side of our orbit. And I'll go ahead and illustrate that point now. Now again, we'll do the same thing. We won't just burn a crazy amount. We're going to go down to a target altitude here first of, let's go back down to 200 kilometers. So I'm going to press the control key and hold it, and I'm going to press the plus key a few times, and you'll notice my PEA immediately starts going down. And let me actually also show that even just using linear translation, I can lower the orbit without even using the full power of the main engines, or without even using the main engines at all. I can just burn, by using the linear translation. I'm pressing 6. I'm putting in a little bit of velocity against the direction of flight, which is slowing me down just ever so slightly. But in order to get to my target periapsis more quickly, I'm going to go ahead and use the main engines. So again, press control and hold it, tap the plus key a couple of times, and you can see the PEA coming down. And when the PEA gets to say 250, I'm going to want to back off the main engine so that I don't overshoot and go way low. But you can see what's happening to the opposite side of my orbit. I'm now down to the orbital altitude of the ISS, but I'm still bringing my PEA down, getting fairly close to the target, 270, 260, 250, 240. And let's kill the main engines now so we don't overshoot. And now we'll just use linear translation just like before in order to get that last little bit of difference. Let's go for an even number, 200 on the nose. Once I get down to like there, now I'm going to go control 6 to give myself even finer input so that I can get a very precise here. And there we are we have a target periapsis of 200 kilometers. Now, in order to bring down this side of my orbit, which I'm at right now, and my current altitude is still 699 kilometers, I need to go around to the other side in order to lower this side. Now, since I'm doing this process, instead of the time to the apoapsis, which is the high point, I need to know how long it's going to take me to get to the low point, to the periapsis. And this is exactly the same as the APT. Here we have PET. That's periapsis time, or time to the periapsis. And again, periapsis is the low point of the orbit. You might also hear it referred to as perigee when you're around the Earth, but perigee only applies to Earth. If you're in orbit around the moon, there's no such thing as perigee. It's actually called paralune if you're in orbit around the moon. So I prefer to use the terms apoapsis and periapsis because they apply to all bodies. So the time to the periapsis is 2,600 seconds. Let's go ahead and warp time forward out to 100, and we'll come around to the periapsis. And again, when we get down to about 100 seconds, we'll want to come out of time warp, and we'll want to orient our vessel. So we're just waiting to get to that point. $500, $400, $300, $200, and we're pretty close. So back to real time. And now we want to click the retrograde button, not prograde, because we don't want to burn into the direction of flight. We want to burn against the direction of flight, so we want to be retrograde. And we give the ship time to settle. It's almost there. Now we're just a few seconds away, 100 seconds away, so it's okay to do just one touch of time warp. Even with the autopilot on, it's okay. And when we get down to about 10 seconds, we'll come back to real time, and we'll do just like we did before. We'll burn just a little bit of main engine, and again, we're using 10 seconds as our figure because we have these powerful Delta Glider engines. If we were using the space shuttle, we want to start this much sooner. Okay, so now just one or two clicks, I press control and hold it, one or two clicks of plus, and you can see that the opposite side of the orbit, the apoapsis, is coming down, and we're past periapsis now. We can tell that because our PET is reset, it's gone back around. So we'll go ahead and add in a little more main engine. And when that gets down to, again, 220, 230, something like that, we'll press the asterisk key to kill the main engine so that we don't overshoot. See our APA coming down. This is what I'm watching, APA. It's the high point of the orbit. It's 280, or 250. And kill the main engine. Switch over to translation. And we'll get the last little bit of difference with translation. But you'll notice here, What's actually happening is that as I press 6 now, it's having this effect where it's bringing down the periapsis a little bit and the apoapsis, and that's actually happening because I'm past periapsis by quite a bit. So I don't really want to do any more correction at this point. So in other words, I didn't start my burn quite soon enough. Instead of 10 seconds, I probably should have started it at 15. And there's no way to resolve this without going back around to apoapsis and periapsis. There is a more advanced way of doing side maneuvers, but we're not going to get into that at all in this video. So that's how we can raise our orbit and lower our orbit. And we have to know how to do that. This is just basic orbital mechanics, orbital mechanics 101. We have to know how to raise our orbit. We have to know how to lower we have to know how to lower our orbit. The very last thing I'll talk about before we move on is the idea of having an orbit that's somewhat imbalanced. Actually, there's a couple of more things I want to touch on, but let's touch on this one first. Currently, our orbit is basically circular. Our high point is a little bit, it's 14 kilometers higher than our low point, but that's not much. Let's quickly just raise our high point way out. So we go prograde because we need to burn into the direction of flight if we want to raise our orbit. And we'll just throw in a bunch of main engine and just raise our orbit to some silly amount. We don't really care what it is. There we go. Now our orbit is imbalanced. And kind of let me clarify what I mean by imbalanced, is that our low point is below the ISS and our high point is above the ISS. So as we go around the Earth, we're actually kind of a roller coaster situation with the ISS. Sometimes we're above it, sometimes we're below it. And that can actually make rendezvous a little bit confusing. So when you're new, and we'll touch on this more when we get into the actual rendezvous video, but when you're new, I would highly recommend that when you're starting the rendezvous, you have your orbit completely below the ISS, like, start at 250 kilometers, or you have your orbit completely above the ISS. If you have one side above and one side below, it's not impossible by any means, but it's a little confusing to new orbitauts. So it's easier if you're below the ISS and you just have to raise your orbit out to catch up, or if you're above the ISS and you just have to lower your orbit down. That it's easier to comprehend what's going on. It's a little bit more sophisticated of a concept when your orbit is above and below the ISS. Now, the very last thing that I want to talk about before we end this video is orbit decay. This is something that you have to watch out for when you rendezvous with another vessel, because what you'll sometimes have to do in order to get the timing worked out, remember we talked a little bit about timing, in order to get the timing worked out, sometimes you actually have to lower one side of your orbit a little bit. If you're not careful, you can actually overdo lowering your orbit to such an extreme that you get your vessel down into the atmosphere, and this is catastrophic. This is this is dead. This is death if this happens and you're not prepared for it. So we're going to lower one side of our orbit down so that we're touching the atmosphere. And how do we lower our orbit? We lower our orbit by turning the vessel against the direction of flight. In other words, we want to go retrograde. So let's go ahead and do that. We'll press T one time just to speed up that autopilot. Okay, now we're facing against the direction of flight. You can see, we're looking backwards. The engines are behind us. We're facing this way. Now we're going to lower the opposite side of our orbit, which happens to be over here. So I'm going to press the plus key and hold it. You can see the APA coming way down. And now our PEA is starting to get dangerously low. It's getting down to 164 kilometers. Let's bring it way down to, say, 80 kilometers. Let's actually go even lower than that. Let's go down to 60. All right, something like that. Now, this might happen to you purely by accident. If you are using Sync Orbit MFD, which we will get into in another video, when you need to work out the timing of the rendezvous, you have to make slight adjustments to your orbital height. You have to either raise your orbit a little bit or you have to lower your orbit a little bit in order to get the timing worked out so that you can catch up to the ISS or whatever body, whatever object you're trying to rendezvous with. If you are not careful when raising and lowering your orbit, you may accidentally, and I've actually done this myself when I was first learning to rendezvous, you may actually lower one side of your orbit so much that you are either hitting the atmosphere or that it's even a subterranean number. Because Orbit MFD doesn't give you, Sync Orbit MFD doesn't give you any warnings about that contingency, about that possibility. It just says that you need to make this much of an adjustment in order to rendezvous with the object. And it doesn't know, or it doesn't take into account what your orbital altitude is. So you have to know how to do this on your own. And this is why it becomes a problem. Let's say that we accidentally lowered one side of our orbit down this much and we weren't paying attention. Now we're saying, okay, we're going to catch up to the ISS. This is us back here. And we're trying to catch up to the ISS. That's our goal. We have our time. We can see our time here, T, 5,235 seconds. We're traveling faster than the ISS, so that means we're going to catch up to it, right? So we're just la-di-da-di-da. We're trying to catch up to the ISS. This is us back here. It's our green line. The yellow line here is the ISS, and we're catching up. Everything's good. But what's going on? Why is my vessel suddenly, it's spinning out of control, and I didn't press prograde, I didn't press retrograde. I'm still trying to catch up to the ISS. And what's going on? I'm losing orbital, or I'm gaining orbital speed, and you don't know what's happening. Well, what's happening is that our altitude here, 81 kilometers, we're now so low in the atmosphere that the wings of the vessel and the tail fin and all these sections are starting to interact with the gases, the gases that are still available at this altitude. Whatever it is, the hydrogen, the oxygen, the nitrogen, all that stuff is up here, and it matters. It will actually, again, if this were the space shuttle, this would be totally catastrophic. And as we continue to go forward, we're continuing to get lower and lower in the atmosphere. And you'll notice our PEA is continuing to go down. This is orbital decay at this point. We're now getting drag as we go through the atmosphere. It's dragging on the vessel, and it's slowing us down, and it's causing our orbit to completely decay. Notice we're at real time right now, and our PEA and our APA are going down. We're basically, because of the atmosphere, we're getting sucked into the Earth, for lack of a better term. We're dragging through the atmosphere, kind of like if you took like you're driving your car down the road and you suddenly go through a really thick puddle. You can feel all that drag that it has on your car. That's exactly what's happening here right now. We're in the atmosphere. We're only at 71 kilometers. If we switch over to surface Earth, we can see that here. And we're going down. We're getting thicker. We're getting into a thicker and thicker part of the atmosphere, and our orbit's getting completely destroyed. Look at our orbit line, look at our apoapsis, look at our periapsis, and if we take a look outside, and if we listen closely, we can hear the atmosphere, and here very soon, we're going to be getting all kinds of plasma built up. As we get down to around 58 kilometers or so, we'll start seeing lots of heat build up around the shuttle, or not the shuttle, but the Delta glider. Down a little bit more. And you can see that pressure wave building up, and now the plasma. And this is just not good. This is not a situation you want to find yourself in. You can see our orbit line here. Our orbital trajectory around the Earth is so far below the surface on this side, that our PEA is all the way down to negative 1,200 kilometers. This is definitely not a situation you want to end up in by accident. And that's called orbital decay. And of course now our orbit plane's completely messed up because the wings were actually, when they get into the atmosphere, they steer the vessel, and it messes up your alignment, and just everything goes haywire and goes wrong. Okay, so I think that basically covers everything that we need to understand about raising and lowering the orbit. It's very, very important to understand these concepts. It's also very important to understand this idea of orbital decay, what's happening right now. So I'm going to go ahead and end the video here. It's been an hour. It's unfortunately a little bit longer than I really wanted this video to be, but there's just a lot to talk about. So in the next video, we'll get into the timing of getting synchronized so that we can catch up to the ISS, so that we can raise our orbit not only to be at the right height, but also so that we cross the path of the ISS at the right time, so that we can actually perform a rendezvous. We'll get into that in another video. If you like this video, go ahead and leave a comment down below. If you like this series, leave some comments down below. It's pretty difficult. It was difficult for me to think about how I wanted to put this video series together, because there's so much to cover, and you just have to be very, very careful not to go into too much detail too quickly, because otherwise it really defeats the whole purpose of having an absolute beginner guide. If you get into all these technical terms about the semi-major axis, and the line of nodes and all that, it's just way too much for people to wrap their head around at the beginning. So I'm really trying to put this video series together and avoid as many of the technical terms as I possibly can until they have to be introduced. If you like the video, again, press that like button. I always appreciate people who subscribe as well. And take a look in the description down below for my Facebook channel, my Facebook page rather, and I put some additional information on there from time to time. And I will see you in the next video. Cases, it's a little more comprehensible if we toggle that to DST, or rather if we press DST to toggle that to the altitude readout. So now it's telling me what my altitude is, not from the center of the Earth out, but it's telling me what my altitude is from the ground up. So from this gray part here up to here is a difference of 206 kilometers. That's what my current altitude is. And I'm going to make that change on both sides. Now what I'm going to do on this side is I'm going to press TGT. And remember, we discussed that when you select targets, you can't press the TGT button and then click on that window. It just doesn't work that way. What we have to do is use the arrow key to go down to, say, spacecraft, and then right arrow over to ISS and hit enter. Now I have the ISS targeted in this MFD, and it kind of might help again to have these separately so that you can see on this side just your ship. This is just the information for our Delta glider, and over here we have both. We have the information for our Delta glider combined with the information for the ISS. Now the reason I want to show this is because it illustrates what the difference is in our altitude. Remember, when we got into orbit around the Earth, we went for an initial apoapsis, a high point of about 200 kilometers. We wanted to hit somewhere in that range. That's generally what you'll go for. If you're specifically going to the ISS, it may not even be a bad idea to shoot for a target altitude of 300 kilometers, because as you can see, the ISS orbits at about 365 kilometers, give or take. Currently it's at 367, the high point's 370, and the low point of the ISS is 357. So targeting an initial altitude of about 300 kilometers may not necessarily be a bad idea. There are reasons to be lower, like we're down here at 200, and we'll kind of get into maybe a little bit of that later. So here we have this issue where our high point is 206 kilometers and our low point is 206 kilometers also. There's only a difference of 600 meters between our high point and our low point. And again, we can also see that over here. And if it helps eliminate confusion by not having the additional data, then you can look at just this side to reference how high we are in our orbit. Now, the ISS is above us by over 150 kilometers. Even at the lowest point, it's still 150 kilometers above us. So what I kind of want to show is a few things here. Obviously, in order for us to rendezvous with the ISS, we're going to have to raise our altitude. And raising and lowering our altitude is the only thing I'm going to cover in this video. I don't want to talk about sync orbit, MFD, we'll get into that later, and I don't want to talk about any other aspect of rendezvous. So we're not actually going to catch up to the ISS in this video. It's going to take, another video out in the future yet, maybe even 2 more before we actually catch up to the ISS. But we need to understand all of the points of raising and lowering the orbit. We need to know how that works. And if we don't know how that works, then we can get into some trouble later on. But before we really worry about raising and lowering our orbit, let's first of all just use a little bit of time warp so we can see what's going on with our orbit stuff here. Now I'm also going to bring up map MFD on this side. Hopefully, you can understand what's going on over here well enough now that you've seen these, now that you saw the orbit MFD without the... Okay, welcome to another Orbiter 2010 video. Today is Friday, July 26th, 2013, and this is going to be a continuation in the video series that I'm putting together that has an emphasis on users who are brand new to Orbiter. I've kind of started calling it the Absolute Beginner Guide. Now, before we jump right into the next part of the video series, I just want to briefly mention that this video is kind of special to me because this is the first video that I'm recording after my lung transplant. For those of you who don't know, I'm just going to cover this very briefly. I was born with a disease called cystic fibrosis. If you're interested in that, you can look it up on Wikipedia and read a little bit about it. I won't bore you with the details. But over the course of my life, my lungs have actually degenerated so much that it was difficult for me to do much of anything at all. In some of my previous videos, if you go back a year or so, you'll see that there were actually a lot of videos where I was struggling just to talk because I was so out of breath that I couldn't even get through the videos very well without just being extremely winded, let alone any type of activity, getting up and taking the mail to the mailbox or taking the garbage out. Any of these types of tasks were just extraordinarily difficult for me. So on June 22nd, around 11 p.m., I got a phone call letting me know that a suitable donor had been found, and this was actually the 3rd time I had gotten such a call, but the first 2 times things just didn't work out. And when they told me when I was going through the lung transplant evaluation process that there would be the possibility of these false alarm calls, and that happened to me twice. But on the 3rd call, I got down to the hospital, called my family obviously, and everything went well. And I'll just briefly put up a couple of pictures here so you can see. This was me with the ISS. That's kind of what we talked about in video 3 and video 4, was how to get into a specific orbit so that our plane would match the plane of the object that we're trying to rendezvous with. Now, being in plane with the object that you're trying to rendezvous with is all well and good, but there are still problems that we have to overcome before we can actually catch up to that object and dock with it. Let's take a look at Orbit MFD. Let's bring up Orbit MFD on this side, and as usual we'll change projection from ECL to ship, which we talked about, I believe, in the probably video 2, I think it was, how in almost all cases when you're new and you're doing things, for starters, in almost all cases you're going to want the projection to be set to ship, and we toggle that just by pressing the PRJ button. Now we will kind of introduce a new concept here, which will be that we'll be able to look at the orbital elements of the ISS in addition to the orbital elements of just our ship itself. And it might actually be less confusing if we do it this way. We'll bring up orbit not only on this side, but we'll have it on this side as well. And these operate independently of one another. So in other words, you can see here I've got projection set to ship, and over here it's set to ECL. These do not conflict with each other. Setting something over here does not mean that it's going to update this side also. These work independently. So what I'm going to do on this side is I'm going to just change the projection of the ship. And actually one thing I forgot to do was to change the distance readout. We talked about that in one of the previous videos as well. Here we have the distance readout is planocentric, so it's telling me what my altitude is, my APR here. It's telling me what my altitude is from the center of the Earth out to my altitude, and that's not terribly useful in most cases. The day after, I believe this was taken just the morning after the transplant, you can see, you know, obviously I'm pretty out of it. I don't really know what's going on. I got a feeding tube stuck in my nose. I've got another feeding tube actually in my neck. They're giving me two types of different forms of feeding because I couldn't eat. The bandages over my chest are actually covering the incisions where the doctor had actually cut across the chest to put the take the old lungs out and put the new lungs in. And here's one other picture I'll put up. This was taken one of the last days that I was in the hospital after all the bandages have come off. Obviously you can see the incisions there around the pectoral area. And so yeah, that's it. That's all I'm going to say about that. It is quite a miracle to me to be able to be here just 1 month later, you know, feeling good and feeling up to talking and doing this video already. I've been missing Orbiter for sure. So that's it. That's all I'm going to say about that. Now, in the last video that I did, which I don't even remember when I recorded it, to be honest, it was quite a while back, we talked about getting into a specific orbit. We talked about how when you take off from the ground, you know, at Cape Canaveral or any other launch site, you can get into a generic orbit, you know, by going to a heading of 90 degrees or some other arbitrary heading. But when you need to get into a specific orbit, which you do need to do if you're going to rendezvous with the space station or if you're going to go to the moon, then you need to get into a specific orbit. So we talked about how to do that, but we left off with our Delta glider. Here you can see, you know, if I kind of come over here a little bit, our Delta glider is now in orbit and it's in plane